I'm a member of IABSE because I value the international perspective that the organisation brings to my career.
Thank you very much.
I enjoyed the event.
Yes.
And I had my first get together with my task group today.
The international character, the network, and also the friends I make.
I am a member of IABSE because of the international contacts and because of the international conferences, the true international character, mixing also academia with practice. And that is the interesting stuff about IABSE.
What's great about IABSE is it really allows me and gives me the chance to interact with structural engineers from all over the world and share what I do and share what they do and learn together about structural engineering.
I'm very glad about it.
Because I love it. I get so much from my profession. I give back so much to my profession, and I learn so much from it.
Yeah, this gives us possibility for international contacts, cooperation, participation in international research projects, and is very, very good for development of bridge engineering also in Poland.
Because I get to interact with structural engineers all over the world.
I like to explore the world.
World Association for Structural Engineers, and where I can find a lot of colleagues from several fields, academics, industry, and so on. So I'm very pleased to be here.
Oh, why am I a member of IABSE? Because I get to meet wonderful people every time I come to these wonderful congresses and symposiums, and I made a lot of great friends and meet the smartest engineers in the world.
I have been a member of IABSE since I graduated in 1981. International Organization in Structural Engineering. It's and also the only organization that is covering all materials, all types of structures. It's covering concrete, steel, glass. I have learned about structural glass from IABSE.
Because it's a unique opportunity to bring together lots of people that share a global passion for constructing new things.
Do you make selfies or photographs?
and to have fun together also in the evenings and to enjoy.
Because I think it's one of the most important international associations in structural engineering and have a lot of great engineers, a great history, and I think it will be a part of the future in the engineering.
The national character of the organization and a nice mixture of materials and products we all do.
Because I'm a structural engineer, I think this is the premier organization for structural engineers. And I like to travel. I like to go to different places. I like the fact that I have met and made friends with people from all over the world, and they're wonderful people.
A little bit of an international background. I've been working in 2 countries. And then when I go to IABSE meeting, I have the opportunity to talk to people of this caliber, like my friend from Israel. I wouldn't meet anywhere in the United States, because that's where I'm doing business now, and it's a great venue for that.
Perfect. And
for me, meeting people from all over the world is a tool for enrichment, for professional enrichment, to hear what is going on around, and maybe to present what we are doing and to impress others.
International contacts I wouldn't have without IABSE.
Perfect, thank you.
So dear colleagues, after this introductory video of the International Association of Bridge and Structural Engineering, I'm very pleased to welcome you part of a wider webinar series of the IABSE. First of all, I would like to introduce myself. I'm Sextos. I'm Professor of Earth Engineering at the University of Bristol in the UK. And I'm delighted to accept the honor to present today as part of this webinar series. I would like, therefore, to thank the organizers for this wider, I would say, series of very interesting talks. A few things about housekeeping, if I may. One is that, of course, this session is recorded, and it will be made available to other colleagues to view it online in the e-learning program of the IABSE. And also that normally it's going to last around 35-40 minutes, followed by Q&A of about 15 minutes or so, depending on how the discussion will go. Therefore, if you have any questions, please feel free to post them in the Q&A session, and then I'll do my best to answer your questions. So without further ado, after this introductory part, start sharing my screen and start sharing my thoughts about the topic we were about to discuss. But before I do so, I would like also to say a few words about the mission of the International International Association of Bridge and Structural Engineering, which, as I said, is of course to organize this series of webinars, but that's not just that. There are many other things that are organized by this very important international society, which of course aims to exchange knowledge and advance structural engineering knowledge around the world. This is done by bringing together people from academia, the industry, the professional construction world, and the research sector. So it's a very important association, bridging more than 2,500 members across 100 countries. Most probably you're already aware of the very important Journal of Structural Engineering International, which welcomes papers from both the academia and the professional structural engineering discipline. And feel free to go to the website and browse the content of this very important and interesting journal. There are also other activities like national groups, task groups, focus groups, working groups and teams that work in different disciplines across materials, structural typologies, and other activities of bridge and structural engineering that are brought together in national group events and conferences. Of course, this was pre-COVID. Now we deal with webinars, but very soon we hope that these things can continue in person so that people can really discuss and interact among each other. There are very important technical commissions as well, dealing with performance-based design, conceptual design, of course, structural analysis, evaluation and assessment of structures, construction methods, processes, retrofit or maintenance, management of existing structures, and of course, sustainability of existing infrastructure. Many conferences are pending to take place. We very much look forward to attending them in person as soon as possible. One in Gent, one in Prague, and others coming along very soon. So this, I hope that it's going to be made feasible in the near future. And of course, the very important young engineers programs. I have to say that I have also been part of it at some point. Probably I'm not as young anymore, but I was delighted to be part of it at some stage because it gave access not only to exclusive material and content, but also the opportunity to interact with other younger colleagues worldwide. So that's a few words about IABSE. And I can now probably start with my own presentation, which is to share some thoughts and the results of a couple of research projects that we had at the University of Bristol on a very important topic, as we think, which is designing, managing, assessing, and maintaining bridges for resilience in seismic region. The resilience is a buzzword, let's say, which is quite popular these days, but we'll try to define it as carefully, as quantitatively as possible for the benefit of this discussion. Of course, I'll be very happy to take questions at the end if you have a different view. There are more than 60 definitions of what resilience really is. So it's really a matter of perspective. I'm very open to discussion on that. But clearly, the way things are at the moment worldwide is that, I mean, the current state of practice is that normally in seismic regions, we follow the probabilistic framework, either explicitly by implementing the convolution of loss, damage, and response analysis and seismic hazard into one loss curve, risk curve that can facilitate decision making, or in a more implicit way through the hidden terms that exist within our design codes, where there is always a probability of exceeding, probability of failing, probability of safety factors and how these are defined and so forth. But these are carefully hidden so that they don't seem too complicated to the common designer. But the reality is that probabilistic framework exists. We design for performance. We set some performance objectives, and we try to satisfy them for different levels of seismic intensity. But clearly, this framework is for one hazard, as we speak, which is normally seismic hazard, even though even COVID has shown that there are more than one hazard that can happen very easily, simultaneously. And we have to cope with all of them at the same time. And of course, this framework is used normally for quick visual inspection, then probably we do a second more thorough inspection, and then we make a decision. So to cut the long story short, probabilities are here. Probabilities are already implemented. And probability theory is effectively driving our decision, blended, of course, with a lot of decision making. Life is more complicated than that because our systems don't stand alone. They're interconnected, as we all know very well. They're vulnerable, as also we know very well, and they're exposed to multiple hazards. So we may lose the functionality of a bridge because of an earthquake, but also because of a fire or because of a flood, because of an accident and any other man-made type of disaster. At the same time, our structures fail naturally, like humans, because they age. So they're corroded, their concrete or steel properties decay in time. There are other things that accelerate the deterioration of their properties and so forth. So we've got in the developed world very extensive infrastructure that keeps on aging and requires maintenance, while this clearly undermines the capability of this infrastructure to cope with seismic loading when and if it comes. So we keep in mind that if we have to deal with a network of things, then clearly a network has many components. Bridges is one of them. Roads is another one. Tunnels, slopes. Anything that can disrupt the functionality of a network is a network component at risk. So this is a very important aspect. And something else that we do know, based on previous experience, is that the direct loss of an earthquake can be very high, of the order of hundreds of billions, of course, as the Fukushima earthquake has shown, but also the loss and cost of the earthquake that is indirect can also be very, very high, even double in this case. Because if the port is not working, if the airport is not accessible, if we cannot really reach from point A, point B, if our services are down, if like New Zealand in Christchurch, the whole downtown is out of operation for such a long period, then the cost is huge, and that's not directly related to structure or bridge damage. Another thing that we know is that the speed of recovery relates to the lack of functionality, but this is not really proportional to the extent of damage. And the reason for that is that you can have a minor failure in the joint or at the entrance of a tunnel, and this is enough to take your bridge out, and your highway, actually, the entire link of the highway out of operation. Similarly, loss accumulates with time. Once the highway is interrupted, it can stay there until it is repaired. And there is a huge cost in diverting the traffic all around this area. For instance, that's a case where not only there has been interruption of the highway, but the bridge also collapsed. So in order to find the closest bridge and do the roundabout, that takes time, takes cost, accumulates with time. Same thing in China for cases where landslides were actually triggered by earthquakes. So that's a secondary effect of an earthquake, but high enough to trigger more than 15,000 landslides and create a very high loss. So recovery is key. Recovery can be quick, like we see in Japan, that from the Fukushima earthquake on the 17th of March 2011, it took about a week to recover, but I can bring many countries in my mind that this would take way, way longer. So recovery, speed of recovery is very, very important. Therefore, the purpose of this discussion here is that we now have started thinking and assess the functionality of the system and not just the structural integrity, whether the bridge has damage or not, And also, we focus on the network and the community impact, and not just on the safety of a single structure. So in a few words, we're zooming out of the problem and we revisit the whole management of seismic risk. And of course, this relates to resilience. Resilience, the most formal, if you like, definition is the ability of a system to rebound, to restore functionality, social life after a major earthquake in the minimum time with a minimum cost. So that's the definition that I personally like to use. Like I said, there are many, many others. Mathematically, this means that if your system was performing 100% before the event and then something happened, let's say an earthquake, then your functionality dropped. And since then, it started recovering faster or slower. So how long it took to recover and how deeply you have failed so that it's harder to recover faster is really a very important question that needs to be answered. And of course, how deeply, how extensively you fail is a function of aging, because if your bridge portfolio or your components portfolio is old, is much sub-designed, substandard designed, if you like, then this means that the loss of functionality will be more significant. Now, the challenges in doing so are several. First of all, how to quantify this? There are so many parameters that need to be quantified, because I'm really personally very keen in defining resilience as much as possible based on some numbers with a degree of uncertainty. And then, of course, this is difficult because it relates to assessing social and financial impact that is not so easy to quantify. Structural damage is easier to quantify. Probably how long it's going to take to repair is easier to quantify. Social and financial impact is not so easy. And then we need to support informed decisions. So we need to be calculating some numbers to help people make decisions and engage, of course, with the professional community and the stakeholders to make sure that our assessments, our numbers, our predictions are realistic enough. Assess and measure community resilience, which, like I said, is quite tough. And then optimize decisions when exposed to multiple hazards, because something that works well for earthquakes might not work as well for floods, for avalanches, for landslides, for pandemics, for transportation issues and other man-made hazards. So how to bounce back stronger? That's tough to say, but all this presentation is about helping cultivating a culture of quantifying resilience. Now, the practical problems here, of course, is that we need to remotely harvest, process, analyze, and continuously update data, because we need numbers. Numbers depend on data. Data are big. So we need to understand them and process them properly, and then convert them into decisions. This can be done by using tools, by, of course, applying probability theory and other analytical tools that we've got, and of course, engage, like I said, with stakeholders so that this is realistic to be implemented. With that, there are two ways to deal with. So there are two levels we can, let's say, intervene. One is before the earthquake event. So we assess how much this risk is for the network level. And then we try to do the best strengthening, for example, or changing our policies before the event or after the event, which is post-disaster management, by minimizing the implications on disaster response and effectively making more successful our recovery schemes. Who cares about this? Of course, that's another question. Is this an academic question that, this is just an opportunity to present the slides in the IABSE webinars and writing papers? Well, that's not true, because we're talking about risk and loss. We're talking about funding. And this means that somebody always has to pay the bill. So the entity that has the responsibility to bear the risk and pay the bill is or has to be interested in minimizing this risk and reducing this bill. And of course, the state is one standard option in most countries. That state is responsible for direct repair cost or indirect social cost. And maybe the highway stakeholders in Central Europe, we know that many portfolios of structures and bridges are privately owned and maintained. So this is the entity that has the risk. The insurance cares, because that's how premium is defined. And also the entities that pay the premium care, because they don't want to pay such a high premium. So this is a huge discussion. Therefore, quantification of seismic risk is so important. That's about pretty much what I'm going to present to you. So instead of just showing a methodology that we have developed, I'm going to show you directly the results of a case study, so that through these results we can understand how our methodology is working. It's not the only methodology. This is just to inspire you mainly. There are other ways to deal with things, but this particular methodology has been defined through a research project entitled RETIS-Risk, real-time seismic risk, and of course it deals with the convolutes, vulnerability, hazard, traffic analysis, consequence analysis, and structural health monitoring, assuming for considering multiple components of the network system. I'm going to take you virtually into Southern Europe, Southeastern Europe, and in Greece in particular, where we will be dealing with a highway that's in the north of Greece called the Egnaria Highway. The interest about this highway is that it's a former Roman path, if you like, that has several numbers of bridges. That's a snapshot of the Roman path. That's how bridges look like. I mean, it's not always so close, the ancient and the modern path, but it's a nice photo, that's why I tend to use it. But the importance of this comment is that there are many, many important structures in an unfavorable topographic environment with quite exposed to seismic hazard. The design PGA in the region is between 0.16 G to 0.24 G, so that's not negligible. Challenging structures, and this is where we try to apply our methodology first. So like I said, I will be talking about the methodology and the case study and the software we developed all in one, so that we see the example directly as we speak. But in essence, the methodology is effectively splitting different stages of things that need to be convoluted. Of course, first of all, we need to map the network in terms of its topology, in terms of the structural portfolios that we've got, the other components that we have, what types of structures do we have, where do they exist, how do they interact with the traffic within the network. We have to map and quantify seismic hazard, and then map and quantify vulnerability and fragility of our systems. And then we have to work with traffic analysis and see if one of the structures fails with some probability, what's going to happen and how this traffic is going to be diverted and how long will it take to recover and so forth. So we set some resilience objectives from the beginning, assuming that we are the stakeholders of this entity. And we say that, okay, we will not accept, in case of an earthquake with a 475 years return period, we will not accept the highway to lose functionality by more than 10% for more than 15 days. I'm giving you an example of a resilience objective. That's not a loss objective, how much it's going to cost to recover. It's a resilience objective, how long it's going to take, of course, how much it's going to cost, and what it will take to restore full functionality. That's a software that we have developed, which is basically an integration of GIS and MATLAB that is doing all the Monte Carlo simulations. And this is how, in any example, we would split a network, highway network area into different components like highways, roads, bridges, tunnels, slopes, and other joints, main cities, points of interest, things that have higher impact, if you like. If you have a very important industry in the region, then this gets a very high weighting factor for the, to retain its accessibility, for instance. And then these critical components are split into joints. These joints are points on the map saying effectively that they can interrupt the traffic within the network. That's the purpose of these critical components, critical nodes in the system. And then we also integrate the travel demand origin destination matrix. So clearly the stakeholder of the highway knows what is the standard traffic in standard days, going from point A to point B and from point B to point C in a matrix and so forth, or at least the average values. And this is also imported into the system. This is pretty much how it looks like. You've got the traffic, you've got the GIS map of the highway. That's the simplest version of the example I'm telling you so that we can understand a little bit better. Bridges are mapped and classified, tunnels the same, and everything else, slopes that can probably pose threat to the functionality of the network. That's how it pretty much looks like. I have to say that all the software runs with freewares. We are not using any professional software. It's using QGIS, but it can be integrated in S3, for instance, ArcGIS and so forth. And then, of course, we need to define the networks of the map. That's how we can see them through the system, where they are. what is their class, what is their coordinates, construction cost, soil type, fundamental period that we're going to use later on, and so forth. We also need to define seismic hazard. Seismic hazard in this case is tricky because it is not the convolution of the probability of experiencing an intensity measure because of the exposure to different faults in a single point. We are effectively talking about the spatial distribution of the intensity because of a single rupture every time. It has to be a scenario-based because for a different location and a different fault that it is rupturing, there is different distribution of seismic intensity and therefore different probability of different bridges and components to fail. So every rupture has to be dealt separately, of course, for different annual exceedance rates that can be applied in different rounds of analysis for different seismic faults and also for different segments of a fault, because a fault has a length of kilometers. And whether you're in this part of the fault or the other part of the fault, it would make a big difference if there's a bridge around. So we're working on a scenario basis, and then everything is integrated in a Monte Carlo scheme at the end. So you can see that we generate number of maps of spatial distribution of seismic intensity for different hazard levels, for different seismic faults, for we predict the failure of different structural components, and we end up with the probability of each bridge to close for a given event. Once we do this, or in order to do this, we need to know, of course, the seismic fragility of the bridges. Seismic fragility, in short, for those who are not very familiar, is the result of a very detailed nonlinear structural analysis under earthquake loading that will give something like the figure in the right, which is a probability to exceed a certain damage state, let's say minor damage, moderate damage, high damage, collapse, versus an intensity measure of the earthquake, see PGA, spectral acceleration, or some other more complicated intensity measures. And by knowing this probability, we integrate that into the system. So we classify all bridges that have the same, let's say, structural typology, therefore the same fragility, and given the location they are in the map and the intensity at this specific location, the system returns back for every analysis of the Monte Carlo scheme, the probability for this bridge to have minor damage, therefore close for X number of days, or moderate damage, therefore close for Y number of days, and so forth. For tunnels, things are a little bit more complicated and also more simple in that the problem has not been studied as much as for bridges, and also that the fragility of the tunnels and all geotechnical works actually depends on different intensity measures. So probably we're talking about permanent ground velocity or peak ground velocity or permanent ground deformation, and not, of course, of spectral acceleration, because there's no spectral acceleration for something that is buried. And of course, limit states are defined in a different way. But there are fragility curves for that. We have introduced them into the system. And then, of course, the software would like to know how long it's going to close each structural typology if it experiences a certain degree of damage. That's also an information that's into the system. And then Monte Carlo analysis will convolute everything with everything in a repetition of analysis. As you can see, different traffic scenarios, different maps, different cases of structures that close the highway and so forth. And this, therefore, will lead to the traffic analysis, because once, for one scenario, 2 bridges are closed, then there is another software that takes care of the redistribution of the traffic load and calculates the extra times that needed for people to drive around and take another route, alternative route. So this is something that is repeated multiple times, again and again, and it's also repeated for recovery phases, because once there is the initial state of damage, then given the repair rates and the duration per damage, per structure, per scenario, we end up, of course, with a virtual time that is running, and after 3 days, 1 bridge opens, so we need to rerun the state of the other bridges and the redistribution of the traffic scenario, and so forth. At some point, which is when we end up with full functionality, everything is green again. But until that, for every stage, we need to repeat the redistribution of the traffic and accumulate all this cost. So this cost, of course, comes from defining an importance function per different highway links based on how much traffic they were carrying before the earthquake. And then we calculate the repair cost ratio index to accumulate how much does it cost to repair these bridges depending on the damage state. And of course, how much is the extra traffic cost because people need to drive further, drive for longer, and so forth. And that gives us the final result, which basically, or the final prediction if we do that before the earthquake, which effectively is explaining the following. These are different hazard levels. So hazard level 1, 2% of exceedance, let's say smaller earthquake. On the other extreme, higher earthquake. If we take no action now, then the accumulated direct and indirect loss is X number of millions, red line. If we retrofit the weak links, like what we currently do actually, we see what are the weak bridges, that's what we retrofit. Then that's the blue line. This is an improvement, of course. And of course, there is the possibility that we don't retrofit anything, but we improve, let's say, our recovery activities, which is not as efficient in this case. And obviously, the green line is the optimum approach, which instead of strengthening the weak bridges or the weak tunnels, the weak components, we emphasize on the links with the highest impact. So these are the components that if they close, they will lead to the higher distribution of traffic, plus higher, of course, structural damage and so forth. And there are different versions of structural and traffic cost. Don't be surprised that in the case of a new highway like the one I'm presenting you, most of the cost is traffic cost because these are all bridges that are brand new. Therefore, it would take a very strong earthquake, in fact, more than 200, 500 years to see them failing substantially. That's why that's a sample that shows that most of the cost is due to minor damage or moderate damage and traffic cost. But overall, in different examples and different bridges, you have different issues to answer. And one of the things that we need to answer is if we know these numbers in advance, would it be better to retrofit now, or we just play dumb, we do nothing, and we wait for the main earthquake to happen if it happens? So this is what I think our comprehensive approach answers, because the stakeholder might take the risk either to do nothing and retrofit nothing, or if it is obvious that there's going to be a very high loss of functionality and cost down the road of the life cycle of the network, then it's much better to pay now, let's say 10% compared to the total risk of paying a 10 times higher cost if a major earthquake happens. This clearly depends on the synthesis, the properties of the portfolio. If there are many old bridges in the system, it's way, way better to invest money now to retrofit, and of course retrofit the ones with the highest resilience impact, not just the weak ones, instead of waiting for an earthquake to happen. Final thing I want to show you in this presentation, before I show some uncertainties of the system, is that we have improved that by introducing structural health monitoring in some of the bridges that we're talking about, because right after an earthquake, we do have a shake map, reducing the uncertainty to zero about how much is the seismic intensity in the system, because we now know that in about 5 minutes. And also by introducing a satellite link. Why satellite? Because typically after an earthquake, standard GSM connections maybe are not working, so that provides a degree of redundancy. So through that, we have the ability to get structural response and measurements from the system, from the bridge, on the bridge, next to the bridge, free field measurements and on-structure measurements that can give us information about how much was this the intensity that the structure experienced. And with that in hand, because we know the intensity and we know the spectral intensity that the structure experienced, we can very quickly after an earthquake predict if there is a damage and if it's worth to go check this bridge or go to another bridge, simply from our stakeholders using the satellite connection before going and checking the bridges on site. Now, a few uncertainties I'm going to share. I'm not going to go into that mathematical detail. You'll see some equations, but I'm going to skip. Only physically, I'm going to share some information with you. One is that in terms of traffic loading, we have to be very careful, because what people are doing before an earthquake is different to what people are doing after an earthquake, after a fire, during the pandemic, during a major crisis. So we need dynamic systems to be measuring or predicting what people would do after an event. So in the numbers that I've shown you, we have several different assumptions for what people do after the event. But as you can see in this figure, 4 different options lead to different predictions. So it is key. The human behavior is key in crisis management, one thing. The second thing I'm going to share with you is a series of uncertainties that qualitatively I'm going to present, because we're talking about loss based on probability of failure. And this probability of failure depends on fragility of the system, which in turn requires very detailed analysis. And there are some very important uncertainties in the analysis of the system. One, what is the stiffness of the abutment embankment system? Because this defines the boundary conditions of the very system we are solving. I'm not getting into detail and talk around the slides, but this is very key to understand that the gap we've got, ratcheting effects, nonlinear response of the abutment, amplification of the abutment level, amplifies and changes entirely both the dynamic properties of the system and the input that goes into the system. One major uncertainty. Second major uncertainty is that soil structure interaction is not just a spring. Needless to say, certainly not a fixity at the base of our structure. So we have developed systems, you can just go to and refer to the presentations, where we introduce a series of LAM parameter models, nicely combine springs and dashboards that are optimized in a way that they mimic the impedance function of soil structure interaction, so that at least the frequency dependence of soil structure interaction is taken care of in an analysis in the time domain. This is really very important to account for. And we can see an example here. So if we were about to model such a complicated 3D pier foundation system or abutment embankment subsoil system, then this is effectively replicated with a series of springs and dashboards that follow the impedance function and provide the frequency dependence in damping in particular, because different properties of the system and the earthquake lead to different soil structure interaction damping, and this changes a lot the results of the system. That's how our finite element model would look like. We also have a software for that, so that springs and dashboards are given very easily to be implemented, so that's not something that people can't use in practice. And effectively, we have also introduced a plasticity model into the system, so that we also take into consideration that when the soil response is nonlinear, then this frequency dependent is further modified, and that can also be captured as accurately as possible. So with this analytical formulation, we're able to capture very well with spring and dashboards something that normally we would need a large soil domain and a very heavy finite element model. And talking about fragility analysis, this requires introduction of uncertainty, requires also a repetition of thousands of analyses. So it makes a great difference if we can reduce the computational cost with a very accurate yet very computational effective set of springs and dashboards. And this is the degree of error we would do. That's for a real bridge in Greece, actually. So if we forget about frequency dependence of soil structure interaction, or we implement it, you will see here that in this axis, if the soil is very soft, and if we're talking about 2x2 or 3x3 pile foundations, and for specific frequencies, then the error, this is the error between, let's say, the accurate analysis SSI and the approximate SSI, can be of the order of 50–68%. And in some other cases, for different damage states, can be even 100%. So we are predicting collapse. We're working to calculate the loss of a system, and we have lost 100% of accuracy because we forgot to include, or we didn't include properly, one important physical aspect. That's my degree of warning here in my analysis, that I zoomed a lot initially, saying that, okay, everything has to be zoomed out. We need to integrate numbers, we need to quantify, okay, fine. But at the same time, for things that have a disproportional effect on what we calculate, we should actually do them properly. Similar type of an issue is, of course, the fact that fragility or damage has multiple forms, and it's multi-angle. because when we have a bridge failing during an earthquake, we can have shear damage of the piers, flexural damage of the piers. We can have the abutments bearing, we can have the bearings failing, we can have the abutments tilting, we can have pounding, probably foundation problems. There are many, many different types of damage. And of course, the severity of damage or the spatial distribution of damage is something different. For that, we have also developed others as well, methodologies for accounting for multiple damage in the system. And also, we observe that this multiple damage changes depending on the direction of loading. And that's natural because the bearings of a bridge that pretty much floats on the bearings in the longitudinal direction are much more sensitive, way more sensitive to this direction of earthquake loading, assuming that the principal direction will be along the longitudinal direction of the bridge compared to the transverse direction, for instance. So depending on what is the damage mode we're looking at, clearly the angle of the principal component of the ground motion, which is something really random, we don't know that in advance, can play a major role in this. So we have to account for randomness in the angle of incidence. We have to account for different damage modes before we end up with a fragility and with an estimate how long it's going to take to recover from a degree of damage. That's also a set of slides that relate to the need of doing large-scale testing, because we are relying very much on doing numerical analysis. And for some important structures, particularly substandard structures, old bridges, it is very important that we have the ability to use experimental data. So I'm going to give you an example of how we have performed hybrid testing, for instance. Why I refer to hybrid testing, not just component testing, because this gives us the opportunity to run the system as a whole by substructuring into numerical components that are run in several computers or several different countries in this case, and some critical elements that in this case are rate dependent and we would like to test, for example, in simultaneously experimental. So that's an example of substructure test between Northern America and Europe. This was done, the test at the University of Patras by Professor Sextos, and we did a numerical modeling and so forth. But the importance of what I'm showing you, because currently real-time hybrid simulation is really advancing, and this was just a simple example that took some years ago to demonstrate the need. This is a capacity that can really help us understand a lot. Things that we can't model, we test. Integral abutments, for instance, soil structure interaction, pounding, how we have impact on stoppers, nonlinear response of substandard bridges, and so forth. Testing, testing, and testing is very, very important. Talking about testing, that's another example of a project that we run in the University of Bristol. This is just to show you things that can be done in scale, but they can combine soil structure interaction on systems that include the soil and the bridge on the shaking table, so we can shake them and measure what's happening behind the wall. Currently, we have a much larger test at the new lab at the University of Bristol, where we'll be measuring within a soil pit of a large dimension of about a room, what would be the passive pressures in the system during loading. And also, this is something that I have discussed previously about multiple angles and multiple damages, introducing and implementing the stiffness properties and damping properties that we have accounted for experimentally. So these are all very important aspects, and something that I would like to share with you ahead of very recent work that we have just accomplished is that when you do all this, coupling experimental and numerical work, multiple damages, multiple types of multiple angles of incidence, different properties, uncertainty in all elements of the response of a bridge under earthquake loading, and we convert everything to money, to loss, to cost, you will see that these results not only are different depending on the angle of earthquake motion, but the stronger the earthquake is, this tends to disappear. That's a very important observation, which means that for some strong earthquakes, or when we're assessing for strong earthquakes, it doesn't really matter that much what is the direction of the loading, simply because there's so many hard modes that are activated due to nonlinear response as the bridge is failing severely, that all types of damage modes will be triggered simultaneously after an earthquake event. And the reason I share this slide with you is to say that some things are important, need to be taken into consideration, but after appropriate research, some others we can safely forget when needed. So it is important when we quantify seismic resilience or seismic damage to be able to do what is needed when it is needed. And these are some further examples. Final thing that we have to keep in mind as we're talking about bridges is that one important aspect of bridge analysis is the fact that ground motion across the bridge is not the same. That's easy to understand because ground motion naturally would change in terms of amplitude, phase, frequency content, and so forth, simply because waves travel and meet different soil profiles and they reflect, refract, are superimposed and so forth. The difficulty is how to calculate that and take that into consideration in a design or assessment process. Because naturally, as we see in this slide, the seismic motion loses its coherence, if you like, its statistical correlation from one point to the other. So if you can see this particular curve, the similarity of what's called the coherency of motion drops with frequency and with distance. And similarly, there are different soil conditions or different side effects, 1D, 2D, 3D, topographic effects, and so forth, that lead to ground motion that is different from one point of the bridge to the other. You cross a liquefiable soil profile, the same. You have significant soil structure interaction within some of your peers, the same, because soil structure interaction would change the frequency content and the phase of the ground motion wherever the soil is substantially different and softer. Therefore, all that combined will lead to cases where the ground motion in one location of the bridge and the ground motion in another location of the bridge is not just that it comes later, it is very, very way different. And that's an example of the Everypost bridge in Greece, where this has been measured by accelerometers that recorded the Athens earthquake on the bridge and around the bridge, let's say free field, in free field conditions. You can see here how ground motion can be very different if you compare one, let's say, recording with another, very, very different. And if you also see the phase properties and the frequency content, that's also different. And to cut the long story short about what is the effect of this ground motion variability, the main aspect is that it triggers higher modes. So if we plot our results, our seismic response in the frequency time space, on the left you see uniform excitation, fictitious, does not exist. On the right one you see the measurements. And you see that there is an extra frequency that has been triggered, an extra higher mode that has been resurrected from zero, and this higher mode has a specific shape, and with this shape, once its contribution is amplified, it affects locally some bridge components. So when we are actually assessing the fragility of a bridge, if the bridge is long enough, if the bridge is on strange topographic conditions, if the bridge is on resting soil profiles that change, are either very soft or they are changing a lot along its length, then this has to be taken into consideration. Another example, I'm going to just show you the slides. Menili Bridge in Greece, analysis, predictions, and then we see what is the performance of the bearings with and without asynchronous excitation. The blue one is way more critical. In some other cases, it's beneficial. It doesn't matter, but in many cases, you can see that the frequency that is responding the bridge is now very different, and therefore the damage ratio can also be different. So talking about probability of damage, that's also something we have to take into consideration. And with this, I'm just gonna walk you through a couple of slides to finish, that this procedure is now one of the solutions that is given in the new version of the Eurocode that is gonna come up really soon. And you can see that there is now a procedure to calculate what are these higher modes that are going to be excited and how they affect specific structural components, and therefore how we can amplify some design quantities safely without doing much in terms of predicting the variability of the ground motion. So it's kind of an offer to the designer to get away with a simple calculation that it's actually capturing some of the detrimental aspects of spatial variability. With that, I would like to conclude by saying that yes, quantification is very important of seismic risk, seismic damage, seismic fragility, seismic resilience. But when talking about bridges, we also have to be rigorous. And obviously, this degree of accuracy is a function of the importance of this bridge. And to close with a couple of conclusions, or if you like, some thoughts. Yes, in my opinion, resilience can be quantified, but we have to balance rigor. We are very, very rigorous in terms of seismic hazard, not very rigorous in terms of geotechnical structural modeling. So this has an effect and can be addressed. Community resilience is a multidisciplinary, a multi-hazard problem, obviously. And sometimes the objectives are conflicting. So we need to have a holistic framework where we both address seismic risk, but at the same time we keep in our head that our portfolio can be exposed to other hazards as well. And either these hazards, a flood probably before an earthquake, they don't happen simultaneously, but they can undermine the ability of a bridge to sustain earthquake loading, so it has to be taken into consideration. Computation is, of course, way beyond power. We need some intelligence. We need to use tools to see within all this data what's happening at the network level, see the patterns that we can't see visually. So big data for decision making, yes, but we have also to map interdisciplinarity, interdependencies between the system. We need accurate tools that will help decision making. And if you want my prediction, what's coming next? I mean, in a practical level, clearly we're going to be dealing more and more with structural health monitoring, more quality data. This is needed, but this is also happening. Large-scale testing, this is needed, but it's also happening. And of course, a lot of work in quantifying resilience. So with these thoughts, I would like to stop sharing, and thank you again, yourself, for your patience, and also the organizers, and I'm very keen to see your questions in the Q&A. So I'll take the questions one by one. First of all, by Maynard Oliver Gonzalez, what are the parameters you consider when you formulate your fragility curve? Like I said, of course, fragility curves are here for many years. Okay, there's nothing new in this. It's a way to quantify the uncertainty and predict the probability of exceeding a given damage state. Fragility curves can be very simplified by accounting only for ground motion uncertainty or some uncertainty in the material properties. In our case, we take it to the extreme, if you like, because we want to have realistic ground motion. I gave you an example about spatially varying ground motions. Realistic soil structure interaction, I gave you an example of how we deal with frequency and intensity dependent soil structure interaction. We try to be as realistic as possible by introducing multiple damage modes, different angles of incidence. So everything that I've pretty much summarized in the second part of the presentation as challenges, this is what we aim to include in our fragility analysis. Feel free, if you're not happy with the answer, to come back with a follow-up. Then an extra question by Theodoros Chaveas, a very, very experienced colleague of us. How did you define cost of particular repairs for the specific motorway and bridges? This was provided by the stakeholder, and it is filtered through existing data from the literature. I follow with your question reading, cost of replacing an expansion joint, a bearing on a high pier, or a plastic hinge formed at the top of a 50-meter pier is significantly different. Yeah, that's absolutely true. The particular motorway has not experienced such damages yet, and no reliable records are available. Also true. So two important comments. One, as I said, we have to filter the existing stakeholder information by what we see in the literature, but you give me an opportunity to say that the way we deal with this cost in the comprehensive methodology we have developed is that we classify bridges that are pretty similar in terms of typology so that we can use literature, if you like, But significant bridges, like the ones that are shown in some of the slides, require bespoke analysis, bespoke fragility curves just for themselves. So you have to run analysis just for themselves. And the same applies for their repair cost ratio. So specific analysis would be needed to account for specific and very important bridges, because clearly these bridges will have the highest impact in the functionality of the system. A bridge with a 5-meter pier, of course, it's a bridge crossing a very steep valley. So if this bridge fails, then it's going to be hard to find another way to cross this valley. Therefore, this, I think I fully agree with your comment, would require bespoke analysis of the system. Feel free to type back. I'm really sorry I can't give you a way to speak up, so I have to read the questions, but let's deal with that as we speak. Comment by Lucas Motion, another very experienced colleague of us. Thanks for the presentation. Is there a catalog of fragility curves available? There's no catalog actually, but there are many papers that provide fragility curves for standard typologies in certain regions. You can find for Italy, you can find for Greece, you can find for the States. For example, the work of Jamie Paget and Deros on standard fragility curves for substandard Californian bridges is a very nice library, if you like, of fragility curves. Same for Europe. Fragility curves exist, so that's not much of a problem. The problem is what our colleague Dr. Chavez mentioned. What if the bridge is special? Then we need a bespoke fragility prediction. Another question, what apparatuses do you install on the bridge you analyze? First of all, we not always have the luxury to structural health monitor bridges that we analyze. In some cases, you just have to go with the design drawings, use the geotechnical investigations, and try to see how you can best model and predict the bridge. One additional comment, it is not just about structural modeling and geotechnical modeling or SSI modeling, it is also about prediction of the profile of the earthquake properties on the site. So you need to have a detailed seismic scenario or a seismic hazard if you're going to run your analysis. Depends on what type of analysis and how you're going to do your fragility assessment. Is it going to be through a pushover? Is it going to be through nonlinear response history analysis? In the first case, that's fine. You don't really care that much about the uncertainty of the ground motion. You're just going to use the spectrum in versus the capacity curve in an ADRS type of an approach at the end. But if you want to assess your fragility based on analysis in the time domain, you will need a suite of ground motions, which means that somebody needs to give you a seismic hazard, disaggregate seismic hazard, give you a set of ground motions that are representative of the hazard of the region, the topography of the bridge, and the soil conditions. So all that combined, obviously, you need it to run your fragility analysis. Now, in terms of structural health monitoring for fragility, it won't help you tremendously before an earthquake event, other in that verifying the dynamic properties of the bridge. So by identifying the structural modes of the bridge, you get a good feeling whether your model is correct or not. And if you can also perform system identification and improve your model so that it matches the natural frequencies and the mode shapes of your bridges, of the bridge you aim to study versus what you measure. This is really, really precious when you have it. And once you've got that, then you can run your fragility analysis. However, remember that the modes that you get by model identification are elastic modes, of course. These are the modes that your system has before the earthquake strikes, and there is no guarantee on how these modes will evolve as the system becomes nonlinear. This is a very complicated, probably the most complicated part of SHM, and therefore, even if you have this information, it will hardly ever improve your fragility assessment. So it can basically improve your base model, your elastic model. And of course, after an earthquake, these are also precious because if you have a baseline measurement before an earthquake and you measure again, you can predict if there is a degree of damage in the system. So this is the usefulness of SHM is tremendous. It's just that it won't help you very, very much in terms of fragility curves, as you ask. There is one more comment by our colleague Dr. Chavez. Some of the major bridges on the particular network have been classified as important and designed with importance factor, correct, which increase the return period of the expected event. Yes. How this is addressed in your computations when compared with bridges classified as normal, they have a different fragility curve. They have been designed for higher standards, and therefore their probability of exceeding the standard damage state for a given intensity measure is lower. So when we integrate everything into the system for the same intensity, a bridge of lower importance will have higher probability to fail compared to another that has a lower probability to fail because it was designed for, let's say, 2,500 years return period. And that's why I said at some point that what you're gonna see in your resilience assessment pretty much depends on the age of your portfolio. New bridges, I mean, if all bridges are new in the system, probably you don't need to do anything of what I've shown. Probably that's not the case. And Egnatia Highway, in fairness, maybe it was an ideal case that we tested because it's a straight highway with many, many new bridges. But we also introduced bridges in the axes that are perpendicular to the highway that were effectively changing some parameters in the system because they included substandard structures. We also, and I showed that briefly, have an example which combines old bridges with new bridges. And then really the question is that we are faced with a real highway in Southern Europe. Do we really assume that we have some money to repair some bridges? Do we really repair the ones that we identify by visual inspection, that they are the ones in need, which is the simple thing to do, or the ones that are exposed to higher hazard, which is another way to see it, or the two combined, which is basically risk, or we run this analysis as I've shown, and we try to identify bridges that are simultaneously weak, exposed to high hazard, and if they fail, they have a high impact on the functionality of the network as a whole. Now, the answer, what are we doing, in my opinion, depends who makes the decision. Because if everything is owned by the state, I take an extreme case, then yes, social cost needs to be included. The state has to pay the bill. The state has to take care of everything. So the state will go to the third option to minimize the loss, minimize the impact, minimize the cost. If the highway is just responsible for repairing a bridge without having in mind the social and financial impacts in the nearby metropolitan city, that's somebody else's problem. And maybe they won't go all the way through to strengthen something that has a high impact. So to cut the long story short, at least in my opinion, the resilience-based analysis depends very much on the properties of a structural portfolio and the geotechnical portfolio, tunnels the same, slopes the same, and about who makes the decision, who is going to pay the bill. That's a practical way of looking at things, apart from the mathematical models and every other nice thing that, or less nice, that we aim to be doing. Thanks very much for your kind comments. Happy to chat offline in any occasion with you. I don't see any other comment, and we are 2 minutes before we close. Like I said, this video is going to be uploaded in the e-learning session of the section of the IABSE webinar series. If you go through that video, you will see that I have included some links to research papers that describe the background of what I've shown. Like I said, other scientists are doing similar or other things. There's no single way to be solving the problem. But probably you get some ideas to blend them with your own ideas and move forward. If you need any additional information, I'm very happy, and I'm posting in the chat my email so that you can contact me directly, and I'll be very happy to talk further with you. Since we need to keep up with our program and our schedule, I think we have reached the end of this presentation. Thank you very much for attending this. And like I said, happy to keep in touch with you.